Hi, everybody, and thank you once again for joining. This is VSA Online in its ninth incarnation, which is really cool. I am really happy about it. And in front of us, we have several really exciting talks. So please consult our website for information. And today, I'm very, very happy to host Alexander Ororbia from Rochester Institute of Technology. And without any further delay, Alex, the floor is yours, please.
Perfect. Thank you very much for that. A nice introduction. So obviously, we'll just dive right into it since I'm a few minutes into this. And my talk is about brain-inspired computing towards neurobiologically grounded credit assignment in biomimetic intelligence. This was motivated by Ross actually reaching out to me about a review paper that I'm not sure if you have read or not. It's not a prerequisite for this talk. I will give you sort of the visual highlights, and you will see references throughout this talk for some nice material, as there's been expressed interest among you in terms of what can you do beyond our traditional deep learning approach to learning and inference. So actually, I have a minor correction to my title, more for fun. It's actually another way to look at it is getting rid of backpropagation of errors, or backprop, which is the workhorse algorithm behind training the deep learning architectures that you know today, including things like GPT and the large language models and generative AI systems that we're all growing more and more familiar with in today's day and age. So very briefly, I'm going to talk a little bit about history, or at least give you a quick history lesson. And that is basically this question of, is AI solved? Or do we have AGI upon us? A lot of those among today's day and age are sort of saying that. We get breakthroughs continuously in machine learning, and we get, again, something that perhaps we've seen before, over-promising that AGI is upon us. And this phrase comes from a paper that I like to sort of poke fun at, although it is a useful paper, is attention is all you need, as you might see at the bottom corner of my screen. And the idea is that transformers are all that we need. And we're seeing a lot of papers coming out these days, like sparks of artificial general intelligence from a lot of big names. For example, you might recognize Eric Horvitz and some other names that have written the textbooks we all know and love in artificial intelligence. So you might be wondering, is AI a solved problem? And the answer is history really just tends to repeat itself. So that can maybe perhaps tell you whether or not we are where we want to be. It was once thought that conscious symbolic reasoning and formal rules were all you need. They might just not have used that phrase. And often criticism of this view was met with ridicule and hostility. None other than Hubert Dreyfus, who I have a couple of his books and some of his well-known work, was one of the earliest critiques or criticizers of symbolic reasoning and good old-fashioned AI, and sort of was arguing for a form of connectionism and statistical machine intelligence that eventually turned out to be right, as that was a useful view later on as we started approaching the 90s. But then again, in the 90s, we repeated again history by saying that kernel machines were all that you really need, and the rise of support vector machines and the beautiful learning theory that goes with it. And criticizing this view was often met with hostility, as we can see at the very bottom. None other than my friend Jeff was often criticized for saying that maybe we should look to neurons and perhaps build connectionist systems. And that was another point in time where that turned out to be right, and deep learning was a useful tool that emerged a few years later, and none other than 2012. I also like to point out we also had some early criticisms from even those in genetics. For instance, Crick often talked about the limitations of deep neural networks today. So we've been here before, is basically the main message. And part of this talk will sort of get at what is it that we might need to reconsider. So again, deep GPTs or deep learning in general are powered by this algorithm known as backprop, and I will spend a little bit of time criticizing it for you and motivating the rest of this talk. But is that all we really need? And a lot of arguments are coming nowadays, and I don't know why my computer keeps moving forward. We have something called red AI, which is what we have today. We have machine intelligence systems that are being trained with extremely large carbon footprints. To build these large language models, we need hundreds of technicians, hundreds of GPUs, and lots of data in the storage requirements meant to hold them. And addressing this is going to be fundamental if we want things that are being advocated for, like green AI and energy efficiency, and if we want to democratize artificial general intelligence. And of course, we also have plenty of generalization issues, as we know that in backpropagation-based architectures, a lot of heuristics that are coming out today are usually to please backprop, to make the process more stable, to work more carefully, and not break. And a lot of tricks are required to get deep learning to even work at all in many cases. We also have things like weak out of distribution generalization. And my lab has done a lot of work in catastrophic forgetting. And I still consider forgetting largely an unsolved problem, although a lot of those in modern day GPT deep learning would say it's a solved problem because we can just pre-train a really big architecture, freeze the weights, and that will remember. And many of those in the VSA HD community would probably laugh at that, as obviously memory is a very important and complex subject and could be the solution to what we need for catastrophic forgetting, but that could be a discussion for another time. So there we go. We have our criticism lined up for deep learning and backprop. We know that that might not be all that we need. We have lots of limitations. Is there anything we could turn to besides backpropagation-based deep learning? And perhaps we could turn to something known as biomimetics, bionics, and modal computation. Now, I'm not going to go into all these details. That's several talks in of itself. But biomimetics is by mimicking or copying or drawing inspiration from biology and bringing that back into intelligent systems to build algorithms that perhaps are more efficient, perhaps addressing the energy efficiency, addressing generalization or problems that maybe we are facing that biological systems like neurons, actual neurons, might be able to solve. So I'm just showing a little bit of work, and you'll see none other than Jeff in there. Those that advocate for a form of deep learning today are also looking at alternatives themselves. And of course, we see things in maybe perhaps drawing from neuroscience. We've seen the phrase neuro AI arise, you might be familiar with. We also have reviews of neuroscience machine learning. This is the paper that actually Ross told me caught some of your interest. So I recommend looking at that. That will actually form the backbone of some of the talk today. We also have modal computation, which, I recommend you go read that 40-page survey if you want to understand what that might mean and how we can get to thermodynamic efficient systems. And of course, there's another longer survey that I would argue is like the companion to the one that Ross might have told you about. It is also like 40, 50 pages, but it goes over the last several decades of biological credit assignment, which I'm going to try to quickly get through in 30 minutes or so. So this is, again, all emphasizing a journey towards biomimetic intelligence, which is sort of the general program that I'm advocating for as an alternative to the modern day forms of deep learning. And we are looking to build biomotivated, self-organizing, structurally adaptive systems. We are also looking to credit assignment beyond backprop. What do I mean by credit assignment? For those that might be unfamiliar, credit assignment is essentially the blame game that we play in deep, complicated computational systems. Let's say we have an objective function and you have a pile of neurons that are associated with leading to outputs that this objective function evaluates. You want to basically say how much each individual neuron is to blame for the values that you observe in your objective function, or how much it's important for improving performance on an objective function. So effectively, it's just the blame game. And the other argument for biomimetic intelligence is that bioplausibility is not simply a niche property solely of interest to biologists and neuroscientists, but this will be crucial going forward for things like energy efficient neuromorphic computing. Those arguments, like, for example, Carl, my friend, and I have made about mortal computers. And then, of course, I like to toss it. This quote will turn out to be the answer to one of the questions I will leave us with at the end of this talk. How much neurobiological detail should we be considering is an ongoing subject of debate, but I like to appeal to none other than Albert. Everything should be as simple as possible, but no simpler. And this sort of becomes like an underlying theme for how much neurobiological detail we bring to the table when constructing biomimetic systems. But let's start, as I motivated you earlier, with what is wrong with deep learning and backprop specifically. So we can start with just the basic premise that even though deep neural networks are inspired by neural connective systems and biological neurons, we have towards the bottom our typical deep learning ANN cell, which is just a pointwise summation or a weighted summation of input signals and run through a particular activation function, even though I have attached a few biological terms like an axon in the cell body. But ultimately, these are very, very gross simplifications of the beautiful, complex neuronal dynamics that I have here on the upper left, where we know we have things like dendritic computation or multiple little dendrites that receive signals from different cells. We have an axon that actually carries an electrical charge across a cell. And so there's a lot of rich dynamics that maybe we might want to start considering how these operate in modeling them and bringing them back into our machine learning systems. And I will briefly touch on throughout the talk spiking neuronal cells, even though we're not going to go into the specific algorithms, as that requires a little bit of background that I don't have the time to go through with all of you. But I'm sure many of you are familiar with it. As I've noticed in VSA, there's a lot of good work on spiking neural nets and spiking dynamics in memory systems. But the real point I just want you to take from this slide is these are very different. And maybe there's something worth borrowing from the richer dynamics of a neuron, especially the fact that they are always inherently stateful and temporal. What do I mean by that? We'll see that as we look at some credit assignment algorithms. Just to quickly review what backpropagation really is, we obviously are taking a weight matrix or a series of weight matrices and perhaps bias vectors. We have an objective function, L of theta. Hopefully you can see my cursor, but it is to the far right, L of theta, which is a function of our parameters. We have some perhaps supervised target, and we compare it to the output of our network. We also have an input vector, which might be pixels of an image. It could be a tensor for a color image. It could be many other representations of other types of data. We plug it in through this pile of linear algebra, get our output, compare it to our target, compute a loss function, and then we just essentially take derivatives of this loss function with respect to each of these WLs. And we basically go back in one long global feedback pathway as we do the chain rule of calculus to compute the requisite deltas to get to each layer, computing the derivative of the loss with respect to each layer, and then through its activation function, and then with respect to its individual weight matrix. Then we ultimately plug this into something like stochastic gradient descent, which I have to the upper left, where we subtract out the gradient and multiply it by a learning rate or something more sophisticated than that. And obviously I have references throughout if you were curious to see like Romelhart's great work that popularized or was part of the beginning of backpropagation of errors. So essentially you're now all experts in backprop if you weren't before. And there's just some expansions, but we're not going to have time to go over that. But the idea is that this form of credit assignment comes with it a bunch of problems. And in that survey that Ross might have referenced you for, we have a couple of key problems. I've already just described the global feedback pathway, which is we have to go through a long chain of operations going forward in the network, and then we have to go backwards across them to get all the derivatives in order. So there is no easy way to parallelize those computations. The weight transport problem, just WT, just so that we were referencing it, is really more of a biological criticism, but it can be potentially practical, where we basically reuse the forward computation or the matrix multiplication going forward to produce the output of a layer. We basically use the transpose of that same weight matrix to multiply error signals in order to compute the chain rule derivatives from backpropagation. In biology, we usually use recurrence, and we have separate feedback pathways. There is no reuse of synapses Not typically. There are backpropagating action potentials, but that's kind of like a very small backwards pathway. You don't go backwards along the same compute pathway that you go to take forward. So that's something we'd like to get rid of. We also have the forward locking and backward locking problems, and I have these illustrated in the middle and right diagrams. Forward locking just means every individual layer of compute, so the activities of these neurons, don't exist, and they cannot be computed until I have all the layers below them, especially data that I plug into my system, whereas neurobiological systems are inherently temporal. They always exist, even if there is no data. And that'll be something we see in a theme of several of the algorithms I'm going to review later. And of course, that means we can't parallelize the inference of our model. We also have the update locking problem, which means I cannot compute the gradient or the update to the bottommost weight matrix until I have computed at least the derivative of our loss with respect to each individual layer. And I need to percolate that backwards using the same operations, but they're transposes going backwards. So that is not easily parallelizable either. And this prevents us from taking advantage of high performance computing in other ways, like parallelism. And of course, I just have this other interesting problem where this is called the forward backward computation problem, or FBD for short. And the idea here is that we are reusing again all the pathways, that we have a separate set of operations that we use to compute error. In this case, these are derivatives that are different from our forward inference pass. And biologically, we use a lot of the same mechanisms that we do inference to conduct learning. And some of the algorithms I'm going to briefly show you today sort of have this property, which is kind of nice. You don't necessarily need to have a separate learning process. You can essentially take advantage of the inference process to guide learning. And then I have a bunch of other problems I'm not going to go into in today's talk, but a well-known one is you need everything to be differentiable. And a lot of the algorithms I'm going to talk about don't require your activation functions, for example, to be smoothly differentiable and continuous. You could be dealing with Dirac delta functions or Heaviside functions or discrete functions or spikes even, which don't have easy derivatives, and we usually often have to approximate them to make things work. And I have some work at the bottom for those that want to like see these problems and more in detail. And then, of course, the last point I like to make is for those that know recurrent neural networks, even though they're not quite in the limelight anymore in the era of generative pre-trained transformers, these problems just get worse. Basically, you take a function, a recursively defined function or a recurrence relation, and you just unfold it into one really, really deep feed-forward architecture, and then apply the chain rule of calculus like normal. So this now, of course, requires you to treat the brain as if it's a time machine, that we could then copy it and staple together all the different slices in time to construct a stretched out version of your brain, and then we compute the updates. This is obviously grossly biologically unrealistic, but also very, very inefficient from a memory point of view. So it'd be really nice if we could learn things that are temporal in nature in an online iterative way, and a lot of these biological algorithms bring that to the table. So hopefully I motivated a little bit of what is potentially wrong with backpropagation or resonate with you in terms of some of the criticisms. But this sets the stage for biomimetics, maybe hinting at that perhaps we're not working with the right kinds of building blocks. That doesn't mean we're going to throw away the tools of linear algebra or even gradients themselves, but maybe we need to construct something a little bit more intelligent to facilitate learning. Backprop is easy to use and rather fast. And that is something that in sequential systems is going to be hard to beat if you're not taking advantage of neuromorphic hardware or parallel compute. Recurrence is easier to just get rid of. I mean, transformers are all about throwing away recurrence and not solving the long-term dependency problem, and using windows or time windows are all that you need. And there's a lot of nice innovations and applications that obviously motivate deep learning as we know it today. And we might have possibly insurmountable roadblocks, like we have energy inefficiency and sample inefficiency that characterize deep learning today. Obviously, I mentioned forgetting and the problems of online temporal learning. Also, sparse rewards are still pretty hard. And depending on if I have time, I might have some fun slides to show you what biological learning might allow you to do in terms of reinforcement learning, which is something that my lab looks at in the context of neurorobotics. Really, the main takeaway message I'd like you to perhaps leave with is we have not tapped into the full value of what nature in biological neural computation and credit assignment might bring to the table. So perhaps we'll look to something other than backprop to train our networks. So let's look at a brief taxonomy of all the possible frameworks. We obviously possibly can't go through all of that in today's talk, but I'll just show you a galaxy of possible neural credit assignment processes. We obviously have backprop, which we all know and love. It's our way of going reverse in our forward chain of computation, but we can resolve things like the weight transfer problem by resolving the backwards pathway and introducing random parameters. We're not going to go into that today, but that is a way to solve some problems. We also have things like representation alignment, which sort of remove the locking problem and the differentiation problems that characterize backprop. We obviously have things like target propagation and recirculation. And these things are covered in that very long survey for those of you that have free time on your hands and want to read the history over the last several decades of biological learning. You'll see that reference throughout this talk. And then, of course, we have other things like competitive learning, which is a really nice property that you can take advantage of. You might be familiar with adaptive resonance theory, and I think that's a very useful mechanism and set of biological mechanisms for learning for not to forget. There's another interesting place where that's useful. And then we're going to actually talk about this one a little bit today, contrastive Hebbian learning and wake sleep, which is another interesting class of biological algorithms. So there's a lot out there, and this slide is usually motivated by Terry Sijanowski, something that he said to me years ago, which is that he believes there's a galaxy of learning algorithms out there. So I sort of generalized that to just credit assignment. And we're also going to talk about this one today, so I'm going to move on. But even though I just gave you a smattering of algorithms that we're not going to even have time to get into, there's way more than that, and we need to organize that. So before we do, we just need to review briefly what we're going to mean by the words postsynaptic and presynaptic neuron. So in biology, that's basically the neuron or unit or neural processing unit that comes before a synapse, not necessarily sometimes like we've taught in classical machine learning, like the pre-transformation, which is a little bit different. That's not before the activation function. It literally refers to geographically a neuron that comes before an outgoing synapse. And then, of course, we have our postsynaptic neuron, which is the neuron that exists on the receiving end of a synapse. And again, you might have a post-transformation, but we're not going to really dwell on this too much. But it is useful to know that a linear transformation is a pre-transformation, and post-transformation is we apply an activation function. This is what these surveys usually do. We sort of dissect these concepts apart. And then another thing to think about learning is really all we're doing when we represent an edge is we're actually modeling a synaptic juncture or a biochemical region between two neurons. This is just the metaphor that we're operating under. And we are ultimately interested in trying to come up with rules that are local in some way to update the statistics or the value or the magnitude of an edge that connects some presynaptic neuron with a postsynaptic neuron, and ideally without waiting for a long chain of operations like we would in backpropagation of errors. And the type of algorithm that you choose sort of tells you how to actually compute that weight change. Some of you might be familiar with something like Hebbian learning, which is just taking the correlation or the activities of the postsynaptic and the presynaptic neuron and multiplying them together. But that rule in of itself doesn't really tell you the entire story, but you'll see a lot of Hebbian-like ideas throughout the rest of this talk. The goal of credit assignment, of course, is to manipulate these scalar edges or these synaptic efficacies or weight strengths. So then what we do in a lot of the work is we sort of break apart all possible credit assignment into a hierarchical family of credit assignment. So on the left is just basically your traditional machine learning pipeline or your computational modeling of an agent. We obviously have an architecture This is maybe something that you don't care to say much about. Maybe you're agnostic to it. Maybe you are not. You have an inference process or some way of querying a probability value or making a prediction or modeling some density or maybe some temporal density. And then, of course, we have data, which is what we're calling our sensory stream. Usually you'll have some task objective. You might or might not have it, depending if you're doing supervised or unsupervised learning. Obviously, optimization is using something like stochastic gradient descent or ascent or Adam or Newton's method or something of that form, like an outer optimization rule. And credit assignment is basically answering the question, how do I compute the change in weights? Not necessarily always telling you what to do with those changes. You can plug them in with an optimization scheme if you want. Sometimes algorithms like Hebbian learning tell you what to do with it. So we will abuse this a little bit. So it's kind of like talking about optimization, but really it's all about how do I compute an instantaneous change to a weight. So there's a lot of algorithms. I'm not going to be able to describe to you every single family in this talk for sake of time. We're actually going to zoom into the very bottom row, and we're only going to pick one algorithm out of each family to make things as simple as possible. So we're going to sample from the bottom discrepancy-based, energy-based, and forward-only based to kind of give you guys a feel for different ways of conducting credit assignment. And that's what we're going to focus here on this slide. And you might recognize this diagram from the survey if Ross did share with you that. If not, you can look it up, a review of neuroscience machine learning by my friends and myself. And we're going to start with predictive coding, which is on the left. So now we're going to actually learn a few quick tricks to do biological learning. To start with, what we do in the several surveys is we sort of talk about learning as optimizing a general energy function. And I know a lot of the group in VSA and HD are familiar with Hopfield networks, so you could use the idea of an energy function loosely as your starting point to understanding how to leave backpropagation-based learning. And what we do is we define some energy function F of some arbitrary set of parameters, theta, and we decompose it into some task objective L, weighted by some parameter beta, some non-negative scalar. And we also have an internal energy model, which is our error, big capital error function, which is also a function of our internal parameters, weighted by alpha. Now, you can recover backpropagation by just basically destroying the internal energy function. So that's what we do at the very bottom of the slide. We just set alpha to 0 and we set beta to 1. And now you're just optimizing with respect to exclusively your task objective, which could be all kinds of things. It could be supervised learning. It could be building an autoencoder to do some form of supervised, unsupervised learning, and so on and so forth. So we do this very briefly in the paper to sort of subsume backprop in a more general class of algorithms. However, basically all the interesting stuff lies in what happens if we don't set alpha to 0 and we learn something about our internal parameters and construct an internal energy function of the neural system itself. This is what also is going to get us for free some local optimization tricks. So we're going to start with predictive coding, which is an example of discrepancy-based learning. All discrepancy is just saying we care about error, but error is everywhere, not just at the output. So those of you that might be familiar with variational free energy, this is a derivative or a derivation from that objective. But ultimately, we have our free energy functional, and we again have an internal energy function. For now, we could just say that we assume that every layer of neurons has some objective function. So here you can see we have a target, which is a set of neuronal activities, which means we need to know the state of neurons at any step in time. We construct some linear function or some local function. It doesn't have to be linear. It's actually typically a nonlinear function of a layer that's nearby. In this case, I'm constructing a hierarchical model. And maybe we have some covariance parameters. Here, I'm going to set them to be a diagonal covariance matrix. We are assuming here an implicit hierarchical Gaussian model, but it doesn't have to be. And basically, if we make a lot of assumptions that I am hand waving away, you can get a L2 distance function that just basically says we are minimizing some mean squared error between a function of one layer of neurons And that means we introduce synaptic weights, maybe dendritic trees or complicated structures, as long as those are locally differentiable. And we compare them to some target neuronal activity. To the diagram to the left, this just equivocates to taking derivatives of just this local error function with respect to either the parameters of our transformation of a nearby layer or the target values themselves. And that gives us what is known in predictive coding as error neurons. And that's what those little orange diamonds are. They are just basically embedding little subtractions that just say, I'm going to take the activity of some target neural layer Z1, and I'm going to make a prediction of it from a layer below. So in this case, I just show you a really, really simple predictive coding circuit. Imagine that we feed in some input data. It basically runs it through a transformation. In this case, you could think of it as just a linear transform followed by some nonlinearity, or maybe you put the nonlinearity at the input layer, and then we make a prediction, and this is the mean of our predictor. We compare it to the current state of the activity value. Say we subtract these two vectors, and now we have an update that we can actually use to perturb the activities of the neurons themselves. And I have a visual, iterative visual. I think that'll make this a little bit clearer. So I'm actually just going to move on to that, as I realize just using my words to describe it might be a little confusing. So for example, we're going to break up learning into two steps that are very different from backpropagation-based learning. Basically, we have an expectation step. For those that might be familiar with the EM algorithm, we are going to compute an update with respect to our activities themselves, which means we're going to change the values of the neurons each step in time. Even if we're looking at static data, these process data through a period of time. And then once we reach some set of activities across the network, we settle. If you know hot field networks, you could think of it as settling to a stable state, perhaps. Then we do an update or an M step or a maximization step by taking the derivative of our free energy function with respect to each individual weights. And the nice thing about this is that all of this can be done in parallel of each other, even potentially asynchronously. And I think, again, this visual will sort of give you a visual intuition rather than working out through the math, of which I will very quickly run out of time if I try to explain every bit of dynamics, and I want to get through the other two classes of algorithms. So let's just imagine, again, we have our simple three-layer system. Maybe input is clamped to the bottom, so maybe we don't need a feedback pathway to connect here. We have some target value at the very top. You could think of this as a label, and at the bottom, we clamp this to some data value. We don't know what the activity of the middle node is, so you could set it to some resting state, such as 0 or some random values. And basically what we do is step one, we generate hypotheses in predictive coding, where basically we make each layer make a prediction or a guess of a nearby layer. So the middle layer is trying to guess the activity values of the top layer. This case, we know it's going to be set to data itself. But notice that the input layer is also trying to guess in parallel the middle layer's activity, which we know at the very beginning is just 0 or some random value. So we make our predictions in parallel at first. This is step one of the E step. Then we basically take the actual value and the prediction, and we compare them. This is what goes inside our diamond arrow. And of course, here I'm trying to biologically illustrate things like inhibition or excitation. In this case, you can think of excitation as adding a value. So we are depositing a signal into our error neuron, so adding it in. If it's a black diamond or a black square, we are subtracting it out. So basically, we subtract out the prediction from a target value, which we know we have values either clamped to the layer or we actually have a resting state value. We compute our error. And then the last thing we need to do is we need to do state correction. So what we do is we transmit these diamond values along a feedback pathway. This can either be set to be the transpose of the forward weights, or you can actually learn a separate signal or a separate error pathway, which we typically do in predictive coding. And we transmit that back. We also apply a subtraction of the error neuron, and we basically update the middle neuron. Obviously, we don't need to update the top and the bottom neurons in this case because those are set to input and outputs respectively. So all we need to do is adjust the middle neuron's activity, and then we basically rinse and repeat. We do this for several steps in time. We go back to step one and we repeat this for however much time in milliseconds you want to simulate your time window. That means we're processing an input and an output pair for a period of time until we settle to some stable state or some equilibrium value, or if you just truncate it after so many steps in time, we settle on a value. And then once we've done T steps of this correction process, then we can actually compute local Hebbian updates, because all we need in parallel is the error neuron that is attached to the prediction made from the middle node. We need the middle node's activity, and we have everything we need to update Wij. And forget about the I and the J. I realized I didn't actually tell you which was J, which was I, and which was K. But basically, you can just take this red arrow here, which is a prediction, and we can update it by multiplying a product of the error neuron and the state activity to compute the update. And we can also do the reverse for the feedback pathway. That is one simple way to learn the error feedback pathway. And we do this in parallel for every layer. So we can compute the update to WKI, in this case, in parallel to Wij, because all I need is the local error neuron in the middle and the input data that I clamped. And then for the output neuron, I need the output error, and I need the middle neuron that we settled to, the activity value. So basically, you get for free a form of dynamic expectation maximization. And this turns out to be a very powerful process that is effectively making you now an expert in predictive coding. You know all that you need to know to build a PC system. So, of course, there's other PC-like systems that I'm not going to review, but target propagation is basically like constructing a chain of autoencoders and sort of doing like a PC-like scheme where we're sort of passing upwards and downwards a bunch of error messages and trying to do reconstruction of layer activities. Local representation alignment, which I refer you to in that reference, is like a simplification of target prop that basically introduces separate feedback pathways that allow you to compute the error neurons without taking T steps. It is a useful algorithm, but the algorithm I showed you earlier has this nice property of parallelism. These algorithms kind of lose some of that to get them to be as fast as backprop, but they're worth looking at. And these are algorithms that sort of fall into the PC family of credit assignment. So that's one way to do learning. I just want to mention very quickly that predictive coding does work with spikes. My lab, among others, has shown how you could translate that to trace values, which is just basically modeling like glutamate concentrations or neurotransmitters, and basically saying that if we have discrete spikes, as long as I'm able to track a trace, which you could say is roughly like a spike count or a spike timing, then we can essentially compute errors in very much the same way that I showed you earlier. But now we get for free the ability to model neuronal dynamics as voltage membrane potentials, and then we can use discrete functions to emit spikes. But for sake of time, I'm not going to be able to go at length about how to do leaky integrate and fire or Izhikevich or Hodgkin-Huxley models, but you could do really complicated things with PC. So for those of you that want to engage with neuromorphic computing, predictive coding does work pretty well with spikes. You could approach biological credit assignment without the notion of errors explicitly, and we could do things in phases. And this is another form of models that, again, lean in on the energy functional family. The idea here is that we're going to actually have to contrast 2 points that we measure our network. So you could think of it again as like a Hopfield network, but we're going to be running this collection of neuronal variables to their fixed points ideally, and we're going to have to model them in terms of a positive phase, which is what I have here loosely described as energy plus, which is the energy function. When I say, for example, clamp to my network's output layer a target activity value, like a label, and an input sensory pattern, like pixel image, and I basically run the network for so many steps in time until I reach a fixed point. And then I also run the network once I'm done with my clamped phase with the input and the output. I unclamp the output, and I basically compute an unconstrained or a relaxed form of my model, where basically I only run it in terms of a free running phase, where I only give it a sensory input pattern, but I don't give it labels. So I sort of ignore the output layer and I let it run for so many steps in time until I run a fixed point. And then all I do is I subtract them. So basically, I'm trying to push the model fantasies, which are in its free running fantasy phase. For those that might know Boltzmann machines, you could think of them as the confabulations of our model. And the idea is our model is dreaming, and we are punishing those dreams for being too nonsensical and unrealistic or divergent from actual real world samples, which is what our positive phase is telling us, behavior that we wish to emulate. And I just show you a very, very simple Hopfield-like energy function, which is just a product of one layer at the L minus one times another layer at L. And we're just basically trying to compute little scalar products. This is just showing you for like the positive phase. C is a variable that I'm just saying is a different set of neural statistics. That means I'm running the model until without clamped output. But really, you could just ignore all of this if this is getting confusing and just imagine that we're going to compute gradients of this cost function or this contrastive energy functional with respect to our weights. And in this case, I just need to get the gradients with respect to the positive phase with respect to the weights. And then I need to subtract out the gradient of this function with respect to the negative version of this energy functional with respect to weights. And what this amounts to is basically an iterative process that kind of looks like predictive coding, at least in terms of the inference. Basically, we're going to run the middle equation, which is just a simplified set of dynamics, where we basically pass along data from the input and the output multiple times until we reach our fixed point. So in this case, we reach what is the gradient of the energy function in the positive phase with respect to our parameters, which turns out that these amount to the bottom equation, which are simple Hebbian rules. All you need is the product of the nearby layer and the incoming layer, and you can just take the transpose and you get for free a little Hebbian rule. So you don't need to wait, for example, percolating backwards from an error function at the output layer. You could do this in parallel for all the layers. These equations too for every layer can be run even asynchronously. So you still get the parallelism resolving the forward locking problem in inference, as well as computing the positive phase. And the negative phase is the same thing. You basically continue running the model. You just omit the labels and you run this for a fixed period of time until you reach a different fixed point or a point where you just say, I call it quits. And we compute a negative phase statistic, compute our gradients, which turns out to just be a symmetric pair of anti-Hebbian rules. And we subtract them out and we just do our contrastive gradient. And that is pretty much it. You have now contrastive Hebbian learning, which turns out is the backbone for things like contrastive divergence, which is a stochastic form of CHL, equilibrium propagation, which just basically changes the nature of when we clamp our label. Sometimes you could run the first phase without a label. You could clamp it in the negative phase instead. And then that's what they call an equilibrium propagation as nudging our model into a different direction. It really is just variations to contrastive Hebbian learning, but the framework rather stays the same. And again, much like predictive coding, contrastive Hebbian learning also works with spikes. I refer you to one of the more recent works that shows how to do this. You can do leaky integrate and fire neuronal systems for those that are, again, interested in neuromorphic implementations. And why do I keep bringing up neuromorphics is that's where you're going to get the big energy efficiency that we seek, because you're going to get in-memory computation, and that allows us to take advantage of the fact that we're working with spikes, which are really friendly for hardware. Again, a subject for another time. But the nice thing about contrastive Hebbian learning is it amounts to or can be shown to be equivalent to something known in biology as spike timing dependent plasticity, which is a Hebbian-like mechanism where we look at the correlation of spikes in the brain to basically compute updates. And that's pretty nice because we have a lot of neurobiological evidence. It turns out you can also do that with predictive coding, but that's, again, a different discussion point. And then I just wanted to briefly mention, so I did promise I'd mention wake sleep. This is a little bit of an older algorithm from like the 80s from Jeff's work, but there was at one point a lot of interest in the Helmholtz machine. Now, I'm not going to be able to unpack all these equations for you for sake of time, as I'm already running the risk of running out of time, and I do want to actually get towards the end. So again, all wake sleep is like a contrastive form of Hebbian learning, but we're injecting noise into our system, and we can kind of decouple the negative and the positive phases in really fun and interesting ways. The last algorithm or family that I want to review is forward-only learning. And if I can try to do this in a minute or two, basically forward-only learning resolves this other problem that I mentioned really early in the talk, which is the difference between forward and backwards computation. Remember, I've said to you earlier that in backprop, we are constructing this like feedback circuitry or this chain of derivatives in order to produce teaching signals so that way we can change the synaptic weights. Well, contrastive Hebbian learning kind of resolves that problem in its own way, but it's really expensive to do so. And predictive coding, as you notice, has to have its own feedback pathway and error neurons. But what if I told you that we could learn or conduct credit assignment using only the forward pass of our deep neural network? And that's where forward-only learning comes into play. It's kind of a more recent innovation. My friend Adam Cohan came up with one of the earliest ones in 2018. And then my friend Jeff in 2022 came up with what you might have heard as the forward learning algorithm. And then 20 days later, I came up with the predictive forward learning process. All of these algorithms at the end of the day do one of two things. We either do comparative learning, which is basically saying that I'm going to have two forward passes. One of them is a function of my input, and one of them is a function of my target output. And I am going to try to maximize the similarity between these two representations. And then I can chain these together to construct a deep architecture that basically looks at comparative learning. So you could use things like I showed here, a cosine similarity. And you do this locally at every layer, so you don't have to, again, transmit backwards across layers like in backpropagation, but you get for free this ability to sort of bias the neural activities of every layer with perhaps an output, like a label. It could be a context. It could be some other signal value that you want to bias the representations towards. But the easiest one to understand is just imagine you have your label, and now you get to bias your network in such an easy way that you can do cosine similarity as an objective. And it, again, can be done locally in space and time. The alternative is contrastive learning, where basically instead of, let's say, looking at an X and a Y and decoupling the representations in terms of those, we are now going to take negative and positive data. So positive data is shown in the top part of this piecewise equation. This is data that we sample. It could be a label that corresponds to it as well. We run this through the network, and that's going to be our instantaneous positive phase. This is the network in a favorable state because we know that the data is correct. And then all you do is you give the network garbage data to get the bottom part of the piecewise equation. Basically, you take data and you manipulate it in some way. And you might be familiar with self-supervised learning, where we apply some type of transformation. Or an easier way is if you have a label, choose the wrong label. So if you have a dog image, label it as a cat, and now feed that through the network. And now you have a negative or nonsense state. And now we can punish the network for those state values. And you have an easy local contrastive function. And that is a different way to do it. Obviously, I'm summarizing a lot of mechanics at a high level, but that is essentially the notions of forward learning. So I described here forward-only learning with Adam's work for similarity-based, and there's some papers that might be of interest to the group. This is obviously, you might be familiar with Jeff's work. So what I described was a form of forward learning. And then, of course, you can actually combine forward learning with other algorithms like the one we reviewed earlier, predictive coding. You can construct feedback pathways and get a time iterative model. And this is what is known as predictive forward learning. And it's a very interesting model for learning recurrent neural systems. And I recommend looking at that for those that might be interested. This turns out to be the basis for the last slide I have for this, which is you can also make forward-only learning work with spikes. My friend Adam did show that the comparative way of doing it, you can train convolutional spiking neural nets. And then more recent work from my lab show that you can take forward learning and you take the notion of a glutamate trace and you can construct really powerful algorithms for learning neuromorphic systems. And this is an algorithm known as contrastive signal dependent plasticity. So hopefully those of you that are interested in the spike versions of these might look into that. These have been out for a while and could be interest to the group. So we've basically now covered everything I wanted, and I have about 7 minutes if I want to stick to our original time frame. So I'm going to go ahead and basically try to explain one thing that I created. So I have a lot of fun slides that show you what you can do. You can learn generative models with predictive coding in a very efficient way. And you can use these for robotics. You can do graph learning. So these are just some cool pictures to sort of motivate those in the group to look at some interesting work on how do I use predictive coding for things like reinforcement learning. And I'll just show you some cool pictures. Like you can do procedural maze learning in a way that's really trivial and straightforward if you build a cognitive architecture. I won't have time to go into that, but you can also do things in robotics. And you can do complicated reinforcement learning and tackle things like the sparse reward problem. But again, to describe how to tackle the sparse reward signal, I would also need a talk in of itself to go into. So I think what I want to do to sort of tie everything together and wrap things up really quickly, my apologies for having to rush through a bit of material, is to think about some challenges and questions. And again, there's a lot of things to think about. I believe that to tackle biomimetic intelligence, we would need to combine these credit assignment algorithms with what I call cognitive architecture prior, because again, this would motivate a lot of the things that are interesting to the VSA community. I do believe in the importance of memory and how do we combine that into a credit assignment framework. And I'll show you very briefly a citation that sort of tries to combine a very, very naive form of vector symbolic architectures with predictive coding known as cog engine, as that's why I believe in a cognitive architecture prior. And again, the principle for biological credit assignment usually is make everything as simple as possible, but no simpler. And this will tell you how much neuronal detail that you need. But I realize that that's not going to mean too much. I just want to mention two things. I think I'll wrap up my talk here. So one is, what is the potential relationship with biological credit assignment with vector symbolic architectures? These are just some thoughts to perhaps motivate those in the community to look into backpropagation alternatives. So I do think that biological credit assignment can be very useful for mapping complex sensory spaces to vector symbolic spaces. So I think, and we've seen all this in recent work where you're combining deep learning as a transformation of raw sensory data to put it into a space that then hypervectors are able to take advantage of. Hypervectors could be loosely described as gross or high-level brain states. So they're sort of characterizing a memory system's operation, and we're putting in different dimensions, have different meanings, depending on how you're encoding and what you're looking at to represent in your memory system. But I think that could be very interesting space of looking at how to take these biological credit assignment algorithms and try to bias the representations they acquire towards hypervectors. And I think that's an interesting space to look at. How to go about doing that is an open question, but an easy place to start is like in predictive coding. These are models that you can actually locally decompose these models into different levels of representation. And maybe there's an interesting way to couple or bias with a prior, like a hypervector prior, the types of representations in the deeper layers acquired in predictive coding circuitry to be compatible with, for example, VSA or HD systems. This is actually sort of a premise behind Cog Engine. I give you one of the more recent references below. This is my work with Mary Kelly, who also gave a talk with me to VSA a few years ago, I believe, where we sort of espoused a cognitive architecture that combined predictive coding with Minerva 2 vector symbolic architecture. Obviously, that's not the more advanced and fancy things that you can do with hypervectors these days, or holographic declarative memory. So I think there's a huge open space for figuring out the role that memory can be used to build for example, generative replay systems that could be used to bias a predictive coding system. I also think that there's a nice bit of integration where, again, in Cog Engine, we offload PC to do the work of like the motor cortex or maybe some visual cortex or procedural memory. And then we use hypervectors or VSA to, for example, model declarative memory or certain aspects of long-term memory that I don't think biological credit assignment alone is going to be sufficient for modeling. I also think that there's a big open space for learning temporal sequential models, which I think is an open question. I mean, those of you with way more experience than I do with VSA might be able to answer how to learn sequences of memory that we could then, for example, construct a vector symbolic representation and learn like a temporal generative model of series of hypervectors that we could then use to replay back to a predictive coding circuit. That's something that's a big interest to me, because what we do in reinforcement learning is we usually store every single state vector we have ever encountered in a big buffer, and then we just replay that to train our backpropagation or biological system. And I think VSA could be very interesting to think about how to construct sequential temporal memories. Again, something I don't have a easy way forward for how to do that, but some in the group might have some interesting thoughts. And then I guess just to wrap up here, obviously I can't thank enough the wonderful people that I have the pleasure and opportunity to work with, and my wonderful PhD students, the 5 of which are in my lab, shown here to the right. And then I have a bunch of names that are wonderful to collaborate with. These are my friends and those that appear in various papers that I have cited throughout this talk. Some names you might recognize. Recently, I got to talk to Ben at AGI 3 weeks ago in Seattle, Washington, where hypervectors are a very, very big and prominent part of the AGI community. So I'm already seeing that language permeate other approaches to intelligent systems and cognitive modeling. And obviously, I can't thank enough my friends Carl and Rajesh, who I work with in predictive coding type approaches, and Adam Kohan, who I also get to talk with in terms of forward-only learning. So the last thing I do want to wrap up the talk is, if you are interested in building your own biological systems or biological forms of credit assignment, you might say, well, that's great. You've reviewed an entire galaxy in a whirlwind tour, a crash course, but can I actually code this up in Python? And the answer is, my lab over the last 5 to 6 years has developed a library to sort of innovate and try to democratize biological modeling to everyone else, particularly with a pedagogical bend for students. So we have an extensive support recently rewritten in the optimized JAX numerical computational library. So we have GPU and CPU support with some support for neuromorphic stuff. If you know of Intel's Lava Loihi, we have some translation layers for that. We also try to reproduce historical models in NGC Learn, and we've reproduced very famous predictive coding, contrastive Hebbian learning, and spiking neuronal systems as well, for those that want to look at the neuromorphic side of things. I want to also just sort of plug in shamelessly to the group. We also warmly welcome community contributions, and something that NGC Learn doesn't really have is any representation from VSA or hypervectors. I would love to have these instantiated as building blocks in NGC Learn. So for those of you that might want to contribute and popularize in a general machine intelligence, computational neuroscience fashion, any of the wonderful work you guys are doing in vector symbolic modeling, I would love to include that. So please consider contributing to NGC Learn. And I think with that, I should terminate my talk. I have reached the end of this, and I will have to go in about 5 minutes, but I don't know if you wanted to take any quick questions.
Thank you, Alex, for the great opening talk. So since you already indicated the time window, so let's be efficient. So questions?
If there's any.
Actually, yes. This is Fred Sommer. I actually have a question, Alex. So yeah, great, very interesting stuff. But maybe so two-part question. So one is, I mean, in a way, you are replacing propagation now by algorithms that have, predictive coding and use memory, but still the level of abstraction and the distance to real neurobiological neurons is almost the same. So my question is, where do you really see the advantages? And the second part of my question is, if you do not literally replace backpropagation, but really allow for some other more biologically realistic learning scenarios like closed perception action loops, curiosity-driven learning,
Mm-hmm.
things like that. I mean, this would still get you in another space. And I think, so do you really, so I think some of the advantages of real brains you can only leverage if you go away from this kind of mainly supervised learning that backpropagation is kind of the paradigm for.
Yes. So both really good questions that warrant even a very long discussion on each of them. So to unpack them, your first question was in terms of the algorithms that I admittedly did also go through very quickly and couldn't espouse more details about. You said that they are at the same level abstraction as backprop. Yes, in some ways they are. We are still, for example, in the ones that I reviewed today, is that they're treating things as like dots and arrows. The only thing I would still say that backprop isn't doing or deep learning systems aren't doing is the neurons aren't inherently temporal, which is something that we are treating now in predictive coding, contrastive Hebbian learning, and even versions of forward-only learning as essentially having dynamics. So we are essentially describing all the neural activities in terms of ordinary differential equations, which is not something that you have in deep learning. I like to joke with my students that the neurons in a neural network don't exist until you run data from the input to the output. Whereas in predictive coding systems and contrastive Hebbian systems, even if you're not putting data in, sure, they might not be doing anything interesting, but they are actually iterating over time. So you have to process everything over a stimulus window, which I do think is a bit of a different modeling approach to treating even static data, because now we have to reach fixed points, but it also allows you to tackle things like temporal streams a little bit easier. But that alone is not, that's like sort of like modeling compartments in a neuron and sort of making them slightly more biologically realistic. I think the place where they get much closer to the neuroanatomy, which I had like no time to talk about, is when you look at their spiking versions, because now we're actually modeling the RC circuits that you could describe basic leaky integrate and fire dynamics. This is also allows you to like start looking at things like dendritic trees, where now we're breaking up synapses into more complex systems. And I think having these local learning rules allow you to apply it to these very rich dynamics that come from modeling things with discrete systems. And the energy efficiency comes from those. So I think, for example, we want sparsity, and the best way to get sparsity is 0 or 1. Hardware loves 0 because we don't actually have to do that compute. And that's the whole premise of neuromorphic computing. We could do this big, grand, asynchronous, parallel computation, because all you need to update any weight in most of the algorithms I explained is just the statistics of an outgoing neuron and an incoming neuron, or a postsynaptic and a presynaptic. So I think that's where you start to see some of those real advantages come into play, is when you start to really consider things like energy constraints, resource constraints, like edge computing, I think is where this stuff really matters. In robotics, this is a big problem because we obviously don't have the big resources to train these big language models, even to run their inference. So I think these algorithms give you that. And even at a high level, they're giving you this layer-wise parallelism that you don't have with backprop.
But I mean, does this really reflect in? So can you do on some benchmark problems really show that this gives you these advantages? I mean, I can see that it could give you these advantages.
Well, by construction, though, like for example, predictive coding is layer-wise parallelizable. Like the dynamics of one layer do not depend on the other layer. So just even from that point of view, now, of course, to take advantage of that, you need to be a richer person than I am and actually have multiple GPUs lying around. because I often simulate these parallel systems sequentially, just because it's not cheap in academia to get lots of resources. But in terms of neuromorphic systems, there's been a lot of work that do show the energy efficiency and the energy gains and the compute power that is afforded by neuromorphic systems. So I think maybe looking at some of my spiking references might scratch at what you're talking about, the benchmarking to look at the actual benefits offered from a practical point of view from these algorithms. Another one that I like to mention that I think is more obvious, and you can kind of use this to construct, for example, systems that are discrete. So backpropagation requires everything to be differentiable, and a lot of these algorithms don't care that you have differentiable activation functions. So this can be very useful. For example, you're working with functions that settle to like discrete representations. For example, with spikes, again, you can't easily differentiate without coming up with some weird approximation. So again, it's kind of nice to eschew this differential ability. Often too in my work, and again, I didn't have time to show all these other results that I have if I zoom in on one of these algorithms, but like you also get these weird properties of generalization. Like in predictive coding, you get better out of sample generalization. And this was some interesting work that we did with like autoencoding of images. And it turns out that even compared to autoencoders trained with backprop, you actually get better performance with these big convolutional systems with PC, that all of a sudden they can actually operate on data points they were never even trained on, where the separation between two data sets is quite great. So you get this weird mismatch distribution performance, and that's something interesting that, again, I don't have too much time to go into right now. So I have shown certain properties of these algorithms by you, something in terms of generalization. In terms of catastrophic forgetting, it turns out that a lot of these biological algorithms allow you to build easier mechanisms that, for example, allow you to integrate memory to combat it. And we've outperformed backprop-based approaches with catastrophic forgetting, but again, that's almost like its own talk in of itself. Just so that way I have enough time to address the other part to your question, is that you said, well, you could also just, instead of worrying about the learning process, which I have my arguments for, because I think it's important that we look to alternatives to backprop, we do work actually with what you were saying about learning to change the outer paradigm. So for example, you said about looking at curiosity-based approaches. That's actually sort of what we do here in this, let's see, with the robotic stuff that I was showing. So like with this actually, and if the slide would actually let me go back, we actually work in a framework known as active inference, which doesn't commit you to a particular biological learning credit assignment paradigm. You could use backprop and active inference, and many of my friends do. But the idea is that this approach allows you to tackle, for example, through a curiosity-based approach, the sparse reward problem. What predictive coding and biological algorithms bring to the table is they allow the individual neural circuits to be learned in an efficient manner. They also allow you to have very, very sparse computational systems, but you don't have to. I mean, you could use backpropagation if you're interested more in like a neurocognitively plausible means of learning. So you can expand the framework out without like necessarily looking at the learning dynamics themselves. But I think the key is that if you're using backprop, you're going to be attached to all its inherent practical limitations. If those don't bother you and those are not of concern, I don't think it's critical. And I don't think you need to do all the modeling of the brain using biological credit assignment. If you're interested in cognitive level questions or behavioral questions or maybe systems level questions, you can use backpropagation as sort of like a placeholder. And the cool thing that I like to mention that I didn't also have time, but those surveys go into detail, is there's a lot of good work that try to show theoretical equivalencies between things like predictive coding and contrastive Hebbian learning and backpropagation. Turns out you can recover backprop as a special case of these algorithms under certain theoretical assumptions. So what that means is that for those of you that maybe aren't interested in saying, I don't want to deal with learning the dynamics of predictive coding, but I do want to know that I could kick the can down the road and swap that in if I wanted to build a biologically faithful system, you can use backprop as a placeholder and focus on things like curiosity-driven learning or looking at memory subsystems. And I think that's useful enough of itself. And then the nice thing is that there's a theoretical transformation that you can make to say that, can I still do this and not be limited by like the feedback pathway problem, the weight transport problem, the differentiability constraints of backprop. So the answer is that you can look in that direction too. And my group has. And some of my students even still, even if most of us try to work around backprop, they do use backprop in some of our active inference approaches, if that kind of answers your question.
Thank you. Yeah.
Well, thank you, Alex, for answering this question. So when you mentioned that, I mean, you were in a hurry somewhere, so I'm not even daring to to ask you questions in the audience.
Maybe we could have a follow-up discussion if you guys want at some point. I don't know.
That would be a good idea. So, I mean, so let's aim for next occasion. So maybe even in the framework of VSAONLINE. Once again, thank you very much for giving a talk. It was really great, and I hope you also would consider sharing the slides so that I can link them from the website, because there were plenty of interesting links. And thank you all for joining this first session. So I see you in 2 weeks from now. Thank you, and
thank you for having me.
Yes, absolutely. Thank you, Alex.
Take care, everyone.
Bye.
Bye-bye.
Thank you. Bye-bye.